awesome car. A little bit more modern. Hey everybody, I'm Nick, and I'm super excited for today's video. Today's video, we're going to be doing relays and switches. I'm going to be showing you how these things work in a 12-volt DC automotive application. And what my goal is to help you figure out how these things are working on your car, on your project, and how you can use them to improve your car and project. I want to lower the learning curve for people getting into automotive repair work or into cars as a hobby, hot rodding or racing or whatever it is that you're trying to get into. I want to help you figure it out. I hope that this video is easy for you to follow. If you have any suggestions or comments or questions, please leave me a comment below, and I'm going to get back to every single comment. And I'd love to know how I can make these videos easier to understand or how I can break things down better. Switches and relays. I'm going to use these basic diagrams to represent relays and switches throughout this video. You have your basic 4-pin and 5-pin relays. These are both Bosch style relays. This one is a typical example. This one is waterproof or water resistant at least. There are several different types of switches. You'll see push buttons, you'll see toggles, you'll see things that screw into heads, you'll see radiator temperature probes. There are pressure switches for power steering and air conditioning systems, fuel systems. There's tons of different types of switches. I'm not going to cover every single possible switch that you'll see, but just know that a switch isn't literally a toggle switch. It can be something that monitors pressure or flow or something like that. This is a temperature probe that you would typically see screwed into the head or the intake on an engine. This is a toggle switch that you might have on the dash in your race car. So I'm going to start with switches because they're a little bit more fundamental. There are many, many different types of switches. Switches have what's called a pole and a throw. So a pole on a switch is, you could think of as an input to the switch. Does the switch have one input, or does it have multiple inputs? So a single pole, single throw switch at its simplest opens and closes one circuit, has one input, one output. Then you have a single pole dual throw switch. You can think of the throw as kind of the output of the switch. Input, output, there can be multiple outputs. So you might have input, output, in the case of a single pole dual throw. Now a dual pole dual throw switch is essentially the same as a single pole dual throw switch, but it has two inputs and probably has 4 outputs in the sense that it can connect to two different outputs. But it does so by one mechanical or electrical trigger. It does so by one trigger, whether it's a temperature probe or a mechanical switch, it does so by one trigger. So you have 2 inputs, which can each go to one of 2 outputs for them. A dual pole single throw switch, essentially the same, except at 2 inputs, 2 outputs, separate circuits. And your single pole dual throw or your dual pole dual throw have a different type of, it's kind of a modified version of them where there's an off position where nothing's connected. And that's actually pretty common. There are more combinations. You can have more inputs than outputs. You can have a lot more outputs than inputs. There's lots of different possibilities, but these are the basic things that you'll see, and this should give you a fundamental idea of what you're looking at when you're looking at a switch. So this is a super simple switch circuit. You have grounds, you have power, and you have this switch that controls flow of electricity to this light bulb. The switch is open, there's no flow. Switch is closed, there is flow. Pretty straightforward, turns the circuit on and off. You can have, in this case, it's a single pole dual throw switch with that off option. You might see this in something like a headlight circuit where you have off, on, high beam. In this case, it's the same thing. Off, low beam flow, high beam flow. Pretty straightforward. The circuit flows in the way that this picture is. The circuit flows through the low beam, turns the low beam on. It could switch and go through the high beam, or it could be in an off position. Honestly, pretty straightforward. I'm not going to go into too much more detail on switches. I just want you to remember and understand that a switch can be anything. It can be in a head, it can be the ECU can be a switch. In fact, an ECU is honestly a really cool switch. It's a smart switch. It's a single pole bazillion throw or a bazillion pole bazillion throw. It has a bunch of sensor inputs. It can have a bunch of outputs, and the ECU can actually have conditions, programmed conditions that turn these on and off, making it a smart switch. So that's actually something very cool. In a couple later diagrams, you're going to see that I use an ECU as a smart switch to control relays in some of these examples. Now this is, getting into relays, this is a standard Bosch 4-pin relay. I'm going to use this diagram to represent it in a circuit. You have a control side of the relay and a switch side of the relay. The control side in a typical relay has an electromagnet in it, and that electromagnet literally physically closes the switch side of the relay to activate the circuit. Now on a typical automotive relay, these are numbered 85, 89, 30, and 87, or 87A and B when we get to 5-pin relays. 85 and 89 are your control side pins. 30 and 87 are your switch side pins. To clarify a little bit, I have this diagram. Typically, I've seen on your switch side, 87 goes to the device that the relay is controlling. 30 goes to either power or ground that you're controlling through the relay. 85 typically goes towards the ground, and 89 typically goes to switched on the control side, or goes to 12 volts positive on the control side. You can switch on the ground. I just want you to be clear, I've typically seen 85 go towards ground and 89 go towards positive 12 volts. The switch can be on either side of those. You could have an ECU on either side, you could have a physical switch on either side. It doesn't matter which side it's on. This is just what I've seen is typical. Most automotive relays don't actually care what direction electricity is flowing through the relay. You could have it backwards in most cases. But there are some cases where the relay has a diode function or a directional function, and the relay does care, so you need to know what you're working with. This is a simple relay circuit. You have your positive power, you've got your battery grounded, you have grounds throughout the system. And in this case, let's imagine that this is a headlight, right? Rather than running headlight power into the car and back out, you can use a relay to control that headlight with one much smaller wire. You have the relay, the headlight, and the battery, for instance, all under the hood of the car. You can supply positive to the headlight and positive to the control side of the relay, and then the control side of the relay can run a small wire through the firewall to a switch that grounds it out and activates the circuit. When the circuit becomes activated, the relay closes and that activates your headlight. That's pretty straightforward, but what that allows you to do is save large runs of big wire. A headlight might draw, let's say, 15 amps for a halogen bulb. You don't want to run that into the cabin through a switch that 15 amps is going to burn up and then back out to the headlight. It's much easier to run it through a relay that's capable of handling 15 amps and then have a little wire, because the control side of the relay will have very small draw, less than an amp, half an amp. You can run a little wire through the relay into the cabin to ground, and it greatly simplifies your control of the headlight. In some cases, this also makes things safer, because now instead of having a 10 gauge wire with 15 amps running through the firewall with let's say a 20 amp fuse, you can have a 5 amp fuse or a 3 amp fuse on that relay, and so that fuse will pop easier if the wire that goes through the firewall actually chafes to ground. So that can be a safety concern as well. In this instance, I want to show you how a relay can be used to control a cooling fan. You might have a switch like this in the head, and it could be on the negative or the positive. There are single pin switches that go straight to ground through the head. Lots of possibilities, but you have the same relay setup, but instead of running through the firewall, we want automated operation of this fan. Now there's no switch that's going to be big enough for, say, a 10 amp or 15 amp cooling fan. And we need something automatic. So we're going to put a little temperature switch in the head or in the intake, right? And then we're going to use that to control a relay, which turns the fan on and off. So we'll have large wires, maybe 10 gauge, to the switch side of the relay, to the fan, to ground. And we can have something much smaller, 14 gauge, 16 gauge, to the temperature switch, through the control side of the relay, to ground. And that just allows the relay and this switch to control the fan in a way that can actually operate completely autonomously. It's very unlikely that you'll find a switch like this that's capable of supporting any kind of decent sized fan, any kind of decent sized load. These switches like very low loads, because what happens is every time they close, there's an arc across the contacts, and the more power that's flowing through, the bigger that arc is, and it's going to burn those contacts up. Now, I want to throw you into having an ECU control something. So remember, the ECU is a smart switch. It's got power and ground, so it's capable of supplying a ground to a relay. Some ECUs can supply positive to a relay, but most supply ground. That's generally preferable and more typical. But so the ECU has power and ground, and it's watching a bunch of sensors. It knows your fuel pressure, it knows your road speed, your engine RPM, your engine temperature. There's just a ton of sensors on a typical ECU setup. So you can use the ECU or an RPM switch or a temperature probe. It doesn't matter what it is. You can use a smart switch of some type to control a relay. In this instance, the ECU controls this relay that activates the fuel pump. When the ECU activates this trigger output, this ground output, power flows through the circuit, closes the relay, turns the fuel pump on. It's pretty straightforward. Now, this is a normally open relay setup. The ECU is not putting a ground on the relay. The circuit is open. This is what's most typical in most automotive applications. You see normally open relays. It's possible to have a normally closed relay, where the relay is actually making contact through the circuit until power is applied to it. And when power is applied to its control side, it pulls it open instead of pulling it closed. This actually has some pretty significant uses. For instance, off the top of my head, I came up with this example. You might have a performance application where you have air conditioning. It's a street strip car. You're going to drive it on road trips or a weekend cruiser. You take it on a power tour, whatever, and you want to have air conditioning in the car. So you have air conditioning, but you know that your AC compressor is not really supposed to turn 6,000, 7,000 RPM like your engine can. You want to make sure that at wide open throttle, your AC compressor turns off if you forget to turn off the air. You can have your ECU control this, or a micro switch on the pedal or something like that. You can have this controlled by an intelligent switch of some type. So the ECU in this example is not putting power on the control side, but the relay is still closed. That allows the rest of the AC system to flow electricity to the compressor like normal, as you would typically have in an OEM or aftermarket normal air conditioning operation. When the ECU does apply a ground, turns on the relay opens, making sure that your AC compressor is off and not turning. There are plenty of other possibilities. You could have something similar that turns your cooling fans off at wide open throttle so that you don't have that resistance during a drag race. There's lots of possibilities the way that you could set something like this up and use the normally closed relay, but this is some of the potential uses as a relay. Additionally, I want to show you that this kind of allows a relay to invert an electrical signal. In this case, we turned a ground into an open. If we go back to our normally open situation, we're turning an open into a close. But you could also use this, say you have a AC kick function, where when the air compressor activates, the AC compressor activates, it tells your ECU, I'm on, and you need to raise the idle a little bit. That's an AC kick function, keeps the engine from stalling when the AC compressor adds load. A lot of ECUs have inputs, and those inputs may have to be negative or positive. Oftentimes, everything on an ECU is a ground. Both the outputs and the inputs are grounded. So the AC compressor is activated by a positive. You can't run that positive straight into the ECU. You need to turn it into a ground. So in that case, you could invert this situation and run your positive through the control side of the circuit to ground, and run your negative a ground to the ECU to tell the ECU, use the relay to tell the ECU that the air compressor, the AC compressor is active. Lots of possibilities like that. I'm not going to go too much further into that. It's pretty straightforward. What I am going to go further into is the 5-pin relay. Now these can be kind of intimidating when you're looking at a circuit that deals with them. They're a lot more complicated. I'm going to give you two examples, one that's pretty simple and one that's more complicated. The 5-pin relay has all of 4 pins that a 4-pin relay has, plus one more. So a 5-pin relay is actually normally closed and normally open at the same time. The 5-pin relay has its control circuit, and it has, on its switch side, it has an 87A that's normally open, just like a 4-pin relay, and it has an 87B that's normally closed. So the way that this works is pin 87B is connected to pin 30 when there's no power applied to the relay. They're connected, they conduct through. When power is applied to the control side of the relay, 87B opens just like a single pole dual throw switch. It opens and it switches to 87A. So this is a single pole dual throw relay. These are often just referred to as 5-pin relays. I've seen them referred to as railroad track relays because they're switching. That seems kind of silly to me, but I've seen them referred that way. And they are essentially a switching relay. They switch from one circuit to another. So here's an example of how that could be useful. Let's say you have keyed ignition and you want to know when the power's on. You want an LED for when the power's on, and you want another LED for when the engine is running. Let's say you want one red for power on and one green for when the engine's running. Now to do that, you could use something like the ECU or an RPM driven switch or something to control a relay. Power would flow through the circuit to your red LED when the ignition key is on, flow through the circuit to your red LED, completing that circuit. Then, when the ECU or RPM switch or whatever determines that the engine is running, it activates this output to activate the relay. The relay switches from its 87B terminal to its 87A terminal, activating the green LED. Now you can see that this is probably a pretty straightforward example of this. There are a lot more complicated things you could do with this. You could have a second fuel pump come on at a certain RPM. You could have a different fuel pump come on. You could have a different fan come on, as we're going to see in a minute. There's tons of things that you can do with this. This is a pretty simple example. Let's look at a more complicated example. So this is a little more intimidating. This is a 2-speed fan circuit. So this circuit uses 3 relays. 2 of them are 4-pin, 1 of them is a 5-pin relay. And what this does is it controls 2 fans to low speed or high speed. This is essentially how an LS1 fan relay setup that you can buy works. I don't like the off-the-shelf setups because they're not heavy-duty enough to run with high-draw aftermarket fans or even OEM fans. I'm actually running this relay setup on my 88 Caprice to control a set of 2010 F-150 fans. I figured if the fans would cool a Raptor, they'd cool my car, and they've worked really, really nicely. Low speed draws approximately 30 amps. The fans are in series with each other in low speed, so they draw approximately 30 amps. And then in high speed, the fans are in parallel. They each get their own negative and positive, and they each draw approximately 30 amps for a total of just shy of 60 amp draw. Now, what that does, it gives me a low speed and a high speed. What it also does, it gives me a quiet speed where you can hear them, but they're not very loud, and a loud speed where you can actually hear them from inside the car. Part of the reason for that is I'm trying to get my car to be as OEM-esque as possible. I didn't want super loud fans coming on and off all the time. The other thing is 60 amps is a lot of load to hit your alternator instantaneously. I would rather step up 30 amps. That's not quite as bad of an increase in load. Not going to make the engine bog nearly as much. And then if it's necessary on a super hot day, high speed can come on, and that's another 30 amps. That's a significant load, but it's not as significant of a step. The engine's not going to be as likely to bog down because the load's not increasing as quickly as instantaneously. I am using my ECU to trigger low speed and high speed. You could use a combination of two radiator probe switches or head intake switches, one for low speed, one for high speed. So this is the circuit with the fans off. Every relay is in its open position. This relay is in its open position with terminal 87B, normally closed, but because the first relay is part of its circuit, it's open. There's no power flowing through any of the fans. When the ECU triggers low speed, it puts a ground on the low speed of this relay, of relay number 1. That closes relay 1 and creates a complete circuit through both fans. The fans are flowing from ground through the 5-pin relay, the normally closed side of the 5-pin relay, through the other fan, through relay 1 to positive, and that creates a complete circuit running the fans in series. Running them in series takes the resistance of both fans, puts it together, causes them to run at approximately half speed in this case, though that's not always a linear increase-decrease in speed. When the high-speed trigger comes on, the other two relays are activated. Now, with the other two relays activated, relay number 2, the switching relay, goes from its normally closed to its normally open contact, and what that does is it creates a ground that only goes to fan 1. Now fan 1 is not sharing its ground in series through fan 2. It has its own ground. Similarly, what relay number 3 does is it closes and it provides positive to fan 2. Fan 2 is no longer sharing its positive through fan 1 in series. Now these fans are in parallel with each other. They each essentially have their own complete circuit from positive to ground. And what that does is it really allows them to flow at full speed. There's reduced resistance. Basically, there's half as much resistance, allowing the fans to run at full speed. Now, the fans are advertised to draw approximately 32 amps in my case, so that is a combined total of about 60 amps. That means twice as much work is getting done, close to twice as much air is being pulled. But these are not always linear, and they're probably not truly linear in the case of my car, whether it's the amp draw, the watts, the amount of air being pulled, the things that you're looking at. But in this instance, it's close enough that you can say we have almost twice as much cooling power on high speed as we do on low speed, almost twice as much air being drawn on high speed as we do on low speed. And this allows me to have low speed comes on most of the time. It comes on with the AC. The ECU that I'm using has an AC input, and that triggers, and it's smart enough to trigger low speed whenever the AC is on. It does that for me, and that makes sure that the fans are running in low speed anytime the AC is on, pulling air past the condenser. And then when high speed comes on, the fans run at full speed. So the only time I've had high speed come on in my case is when idling for like 45 minutes with the AC on and it was like 95 degrees out. Normally I don't ever see high speed come on, but you might, depending on what kind of radiator and fan package you're running in your application. The point that I'm getting at is this is a pretty typical, pretty solid example of how you would see 4-pin and 5-pin relays used, and in this case in conjunction with each other. When off, the circuit's non-functional. Low speed triggers one relay, putting the fans in series. through the normally closed contact of the 5-pin relay. When the other two relays are activated by the high-speed trigger, the normally closed circuit is opened and the normally open circuit is closed, providing a unique ground to the first fan. The third relay, the last 4-pin relay, when it's closed, it provides a positive to fan number 2, allowing it to have its own complete circuit. There are many different ways you might see switches and relays used in a 12-volt setup. If this video has helped you, please give me a like and subscribe. I'm trying to do more videos like this to help people get into the car hobby, to get into hot rodding and building cars and enjoying cars and just building cool stuff. If you have any questions, I'll do my best to answer every single question. Whether you're looking for clarification on something or for me to go more in depth on a specific topic, please let me know. If you have a specific application question, I would be happy to try to make a helpful suggestion to you. I hope you've enjoyed this video. Also, leave me a comment and let me know what topics you'd like to see me cover in the future and what more you'd like to see me do in these videos. If there's anything I can do to make these videos better or easier for you to understand, easier for you to watch. Thanks for watching, and catch me next time.